The new topic is entitled The Rank of a Matrix. We'll ultimately talk about the rank of a matrix. Let's give the definition first. Let A be an n by n matrix. If we consider each of their m rows as a vector in Rn, we can think of something. If we consider each of the m rows, of A as vectors in R, because each vector, each row, has n entries, hence the n columns. 1, 2, 3. I don't care what I put. Let's look at it. It has 1, 2, 3 entries, which also happens to be the number of columns. You have a second row, 2, 4, 5. It too has 3 entries, which corresponds to the number of columns. We have n columns. Each vector is in Rn. In my case down here, n just happens to be 3. Okay, now, what about the span of these vectors? Then the span of these vectors, which vector? The rows, each row we're going to think of as a vector. Okay. The span of these vectors happens to be a subspace of Rn. The span of these vectors, I just want to change one word. Then we call the span of these vectors the rank, or the row space. Row space of A. It has a matrix. It has some rows, number of rows, whatever it is. In my case, I'm calling it M. The span of these vectors, the span of those vectors is called the row space of A. If we consider the n columns of A as vectors in Rm, then we call the span of these vectors, which is a subspace of Rm, the column space of A. Okay, so here I defined the row space of A and the column space of A. I'm going to state a theorem. Theorem says that if A and B are row equivalent, then the row space of A equals the row space of B. The row space of A and B are equal. Okay, I'll formally write that up in one moment. So you can reduce A to matrix B. They both have the same row space. They're equal. Wait for this eraser to catch up, and like I said, I'll state it. If A and B are the same size, are two m by n matrices, two m by n row equivalent matrices, then the row space of A and B are equal. Try this a third time. A nice ego, or equal. The span of the rows is the row space. Now, if you think about that, that is obviously true. Because how do you go from A to D? You add one row of, you add a row of matrix A to another row of matrix A, and that gives you matrix B. You can also multiply any row by whatever you want. These maneuvers do not change the row space. Okay, adding row I of matrix A to row J of matrix A will not affect the row space. You still get the same span. The linear combinations don't care about these adding one row of A to another row of A. Okay. So how about we consider this problem? Suppose we have this set of vectors. Let S contain the vectors v1 through v4. v1, v sub 2, v sub 3, v sub 4. Where v1 is 1, negative 2, 0, 3, negative 4. V sub 2 is 3, 2, 8, 1, 4. V sub 3 is 2, 3, 7, 2, 3. And V sub 4 is negative 1, 2, 0, 4, negative 3. And also let V be equal to the span of S. This is S, V is the span of S. Of course, the span of S will be a subspace of each vector is in R5. Okay, so we want to find basis for V. Find our basis for if you want to find a basis for V, you write down the matrices, the vectors of V as rows, vector 1, vector 2, etc., and then you reduce. -1, 4, -3. This first row is vector 1, V2, V3, and V4. And if you reduce this, you will get the following. Reduce means RREF form. If you were to reduce it, you will get this. Now at this point, you're able to find the basis. It's the spanning basis. Just ignore the rows that are 0. The following. The vector is 1, 0, 2, 0, 1. It's this vector and the next vector. That was the next vector, and then the third and last vector. If you haven't caught it yet, what reducing a matrix does is get rid of the dependent vectors. Of course, these vectors span S. It is S. But to make it a basis, we want to remove the dependent ones. And it turns out that this last row, I mean to say, since this became a row with zeros, that means that this vector, the fourth vector, is a linear combination of the others. Okay, that is, V4 is some multiple of V1 plus some multiple of V2 plus some multiple of V3. Now, since V4 is not all zeros, I know for sure that not all of these C's are 0. Because if all of those C's were 0, the right side would be 0. 0, 0, 5 times. It'll be the 0 vector in R5. So at least one of them are not 0. I'm going to make a point here. At least one of them is not 0. For argument's sake, let's suppose that C2 is non-zero. Suppose that C2 is not 0. So solving for C2V2, we know that C2V2 is, well, we have V4, 1V4, bring this over, minus C1V1, bring this over, we get minus C3V3, and since C2 is not 0, I can divide by C2. So V2 is this scalar times V4 minus this scalar times V1 minus this scalar times V3. That is, all I'm trying to say is we could have eliminated that second row. Okay, if we would have interchanged row 2 and 4, and in fact, to get V4, C2 was not 0. If we were to interchange row 2 and row 4, then this vector would have become this vector. When we reduced it, this would have been all zeros. That is, the answer would have been the basis is 3. The basis is not unique. The basis is not unique. And once again, there is a basis. Notice what I said carefully. There is a basis. Okay. So, I'm going to look at this again. The matrix A and what we got in reduced row echelon form. And then I'll say something that can make it a little bit easier. But remember, when you have a basis, you can write, for some set, you can write any vector that's the linear combination of the basis vectors. You have a set V, and you have a basis, you have a vector space V, and you have a basis for V, then every vector in V can be written as a linear combination of the vectors in. So let's look one more time at these two matrices. A happened to be 1, negative 2, 0, 3, negative 4, 3, 2, 8, 1, 4, 2, 3, 7, 2, 3, and negative 1, 2, 0, 4, negative 3. And this was row equivalent to this matrix. 10201, 0, 1, 1, 0, 1, 0, 0, 0, 1, negative 1, and a row of zeros. Okay. Let's look at the leading ones. In row 1, that's the leading one. In row 2, that's the leading one. In row 3, that's the leading one. And row 4 had none. So column 1 had a leading one underneath it. Column 2 has a leading one. Column 3 does not. Column 4 does. There it is. And column 5 does not have a leading one. So column 1, 2, and 4. Columns 1, 2, and 4 each have a leading one. Now, this is very important because if we take our vector V equals, say, I don't know, A1, A2, A3, A4, A5. And remember, we had that basis vector. This basis 10201. Call the second vector W2. And the third vector was 0, 0, 0, 1, negative 1. Okay. That's the basis. basis was there. Now, what you can always do is say that this vector v is aj1 times w1 plus a times j2 times w2 plus a times j3 times w3. Now, the obvious question is, what's j1? What's j2? What's j3? Well, the j1 and the j2 and the j3 in numerical order are the columns that had a leading 1. Well, column 1 had a leading 1, so I write a1 plus column 2 had a leading 1, so I write a2, w2. Column 3 did not have a leading 1, but column 4 did, so I write down a4. This a1 is that first number in the vector. This a2 is the second number in the vector. This a4 is the fourth number in the vector. So, try to sneak it in. But if v is equal to, I don't know, 3, 7, 2, 4. Let me put a 5 in the front. So I'm going to get some number times w1 plus some number times w2 plus some number times w3. What are those numbers? Well, again, column 1, column 2, and 4 had the leading entries. So first I put down the column 1 number, then I put down the column 2 number, and then I put down the column 4 number. And there it is. There it is. There, you may say, well, what's W1? What's W2? What's W3? It's the vectors that form the basis for V was the span of S. Okay, so let's do one more numerical example, and then we'll kind of do a whole nother problem just like 3, 5, 1, 4, -7. Well, since the columns, I'm looking kind of up here now. The columns that had a leading 1 were column 1, 2, and 4. So column 1 and 2 and 4. Those are the coefficients. That this first number times W1 plus this second number times W2 plus, now let's make that a 14, plus this fourth number times W3. And work it out. It will work. Of course, this would have to be in the span. Okay. So, I'm going to make believe something that I'm about to write is true. The concept that matters, not what that's just going to say is going to be grossly wrong, but I'm going to say it anyways. So I'll put down a matrix. I'll randomly say it's row equivalent to another matrix in RREF form. which most probably will not be true. 7102143142873014227, -20, -8, 4, -111. Suppose that this matrix is row reduced to the following. I have 6 columns. And I'm gonna pick, say, these 4 that have leading ones. So column 1 will look this way. Column 2 will look this way. Column 4 will look this way. Column 6 will look that way. And here I'll have 7, 2, 0, 0, 0, and 3, -4, 0, -7, 0. So this is make-believe. Make-believe. It'll be unbelievable if that's true. Okay, because I randomly wrote it down. Let's just make believe that this is true. That these 2 matrices aren't in fact row equivalent. And the last one, the right one, is in RREF form. So now, the basis for the span of S. Now, what is S? S is, maybe I should have written it down. S is vector 3, vector 4, where that is vector 1. That is a whole row. What I just circled, the box, is vector 2. This here is vector 3 and vector 4, and then lastly, vector 5. So what is the basis for the span of these vectors? And the answer will be the column that had leading ones. The columns that had leading ones. The first, the second, the fourth, and the sixth. Okay. Which means we come here. Column 1, column 2, column 4, and column 6. That's a basis for the span of those 5 vectors. Now, I want to rethink what I'm saying, please. Okay, no. Sorry about that. It's the rows that are not 0. Sorry. It's the rows that are not 0. The first row is 1, 0, 7, 0, 3, 0. The second non-zero row is this one, and the third non-zero row is this one, and the last non-zero row was this one. That's the basis for the span of those 5 vectors. If I just gave those 4 vectors are, there's 5 vectors, sorry. And I ask you, what is the span, what is the basis for the span of these 5 vectors? What you should do is write down vector 1 as the first row, vector 2 is the second row, etc. In fact, you can do it out of order. You can do it out of order. Reduce it. Now this matrix, to be honest, is not in reduced RREF form because I rarely should put the row of zeros on the bottom. Make believe I just did that. Well, the resulting matrices, the non-zero rows, make up the basis. Okay, so now we have our basis. Okay, and let's suppose V is equal to 1. And for simplicity, let's call these vectors in the basis W1, W2, W3, and W4. Well, it turns out that this is going to equal to some multiple of W1, or can be written as some multiple of W1 plus a multiple of W2 plus a multiple of W3 plus a multiple of W4. Okay, now since column 1, 2, 4, and 6, I circled that. Column 1, 2, 4, and 6 all had leading ones. 1, 2, 4, and 6. These are the numbers. 1 goes there, 1 goes there. Coincidentally, they're all 1s, but they didn't need to be. So I found the linear combination of the basis vectors that give me V. How did I do that? I looked at column 1, 2, 3, and 4. Sorry. Column 1, column 2, column 4, and column 6. The one that had a leading 1. Column 1 does, column 2 has a leading 1, column 4 and column 6 have leading 1s. And none others do. Okay, and it didn't matter that I didn't reduce it correctly. Just make believe. Maybe what I should have just done was say, here's matrix A. Here is matrix A, and it reduces to what I have on the right. Just call this matrix A. It is a 5 by 6 matrix. And give her definition, and then we move on. Dimension of the row space of matrix A is called the row rank of A. Likewise, the dimension of the column space of A is called the column rank of A. So either you read everything that's in brackets or you don't read everything in brackets. If we were going to read everything in brackets, the dimension of the column space of A is called the column rank of A. We are going to read what's not in the brackets. Dimension of the row space of A is called the row rank of A. I'm going to give you a matrix, and we're going to find the basis for the row space. To save some space, I'll just write down the matrix A. I won't write down the question. And maybe in the bottom I will. Find a basis for the row space of matrix A that contains only row vectors from A. Okay, so here is A. 1, 0, 3, 1, 2, 2, 1, 1, 4, 5. I want to find a basis for the row space, but I can only use vectors. This basis can only contain row vectors from A. So what you want to do is remove the linear dependent vectors. And one way to do this is to solve the following. Solve C1 times the first vector plus C2 times the second vector, 2, 1, 1, 4, 5, plus C3 times the third vector, plus C4 times the fourth vector, and you want this to, let me put it here, you want it to equal the 0 vector in R4. To save a little space, I'll write the 0 vector. I'll even put sub 4, the 0 vector in R4. Now, we don't really have to solve it, but if we were, we would write down vector 1. We'd write down, that is this vector as a column vector. The second vector is a column. We basically write down the transpose. And we want to reduce this. We want to see what vectors remain. And when I say we're not literally going to solve this equation, meaning, although I'm writing it now, I'm going to erase it, we don't have to do this. We don't have to write this at all. We just want to see what vectors stay. We know that those 4 vectors span the space of those 4 vectors, but can I get a smaller set? And now, if we were to reduce this, it, we will get the following. 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, and then 2 rows of zeros. First row has a leading 1. The second row has a leading 1. The third row has a leading 1. The next 2 rows, being all zeros, they have no chance of having a leading 1. Now you look up and down, you look up column 1, and you say, yep, it has a leading 1. Column 2, yep, it has a leading 1 in it. Column 3, yep, it has a leading 1. Column 4 does not have a leading 1. You may say, of course it is. There it is. No, it isn't. The leading 1 comes from rows. In row 2, this is in row 2. Row 2, the first non-zero entry is obviously that one. That's not a leading 1. Okay, so column 4 did not have a leading 1. Column 1, 2, and 3 did. Oh, so now we have the answer. The basis for the row space. Okay, now notice, each column 1, 2, and 3 we're concerned with. That is column 1, 2, and 3. The fourth column is out of the picture. Okay, and these columns, including the last one, those were the original vectors. Those were the original vectors. The column space is just those 3 vectors that I just circled now. The ones that came from column 1, 2, and 3. Not of this matrix. Not of this matrix, but the other one. Okay, so it's 1, 0, 3, 1, 2. 2, 1, 1, 4, 5. And 1, 0, 1, 2, 4. These, oops, put brackets. These 3 vectors span the row space. And they're linearly independent. I know they're linearly independent because I was able to conclude that I didn't need this last one. I was able to conclude I didn't need the last one. If you were actually going to solve this one, you are actually going to solve it, and we let C4 be R. Or X4 be R. So X1 would be, well, let me not write it that way. X1 will be negative R. Because 1x1 plus R equals 0. You bring the R over, you get negative R. X2 is negative R. X3 is 0. X4 is R. Okay. They're all in terms of R. They're all in terms of R. R is not independent. R is not independent. You had to remove it. Or maybe I should say X1, 2, and 3 depend on R. Okay. Now, what we can say is the row rank of A. That's the dimension of the row space. Well, a basis for the row space is these 3 vectors. So the dimension will be 3. Finding the row rank of A is pretty simple. After you find the basis for the row space, just count the number of vectors in the row space. 1, 2, 3. And that's the row rank of A. That's the row rank of A. We're going to keep this same matrix at the very top, but the question is going to be slightly different. Now state the new question. Okay. You want to find the basis not for the row space of A, but the column space of A. Well, I want to remove their dependent columns. So basically what I want is C1 times the first column, 1, 2, 1, 3, plus C2 times the second column, plus C3 times the third column, plus C4 times the fourth column, plus C5 times the fifth column. And there should be parentheses on an exam. Definitely put them. And I want this linear combination to give me the 0 vector in, they're all in R4. All the vectors are a 4 tuple, 4 numbers. So they're in R4. Okay. Well, if you want to solve this system of equations, what you do is you write down the vector as a column, the second vector as a column vector, same with the third and the fourth, and if you realize, you just get back matrix A again. This is exactly matrix A. It's exactly matrix A. And we reduce this. We just reduce this. And it reduces to the following. Reduces to this. So all we're concerned about are columns that have leading ones. Row 1 has a leading 1. Row 2 has the first non-zero entry. Row 3 has our first non-zero entry. Row 4 does not. Well, when I look up and down column 1, I find a leading 1. I boxed it. Column 2 has a leading 1. Column 3 has a leading 1. Even if that number was 1, it's not a leading 1. Column 4 does not. Likewise, column 5 does not. Coincidentally, the first 3 columns. Okay, we're done. I go to the original matrix A. Well, that's not true. I go to the matrix I just circled, which happens to be A because we're doing column spaces, and I say that's the basis. Those 3 columns are the basis. The basis for the column space of A is those 4 vectors. The first column, the second column, the third column. Now, again, haven't done this in a bit. Let's talk about what this means. We're talking column spaces. So you have those 4 columns. And you can take infinitely many linear combinations of those 4 columns. Okay, and imagine this here is R4. The span, 5 columns. The span of those 5 columns will give you a subset of R4, or possibly R4 itself. Or let's say a subset. Now, do you need, these happen to be the same columns, do you need all 5 of these vectors to take linear combinations of to get all of these vectors in here and nothing outside of there? The answer is no. You don't need the last 2. The span of just these 3 vectors gives you the span of all 5 of them. And those 3 vectors, or 3 columns if you prefer, are linear independent vectors. So you just need these 3 vectors, and if you take the span of those 3 vectors, you will get every vector in here, their initial span. This here is the span of those 4 vectors. Those 5 column vectors. This is the span of those 5 column vectors. There are beginning ones up here. The span of those 5 column vectors give this set. Okay. 2 comments about these 3 vectors. They also have the same span, and they're independent, linearly independent. That is why they are a basis. I'll state a theorem, and I'll update our definition. And I want to make one comment here. I want to make one comment right here. The dimension of the column space is 3 because the basis had 3 vectors. Recall when we took the same matrix A, and we found the dimension of the row space, it was also 3. In fact, that's always true. It being the row space of A and the column space of A are always equal. And we're not going to prove that. But the dimension of the column space and the dimension of the row space are equal. Remember that the dimension of the row space, by definition, was row rank. The dimension of the row space is the row rank. The row rank of A is equal to the dimension of the column space, which is the column rank of A. The row rank of A and the column rank of A are equal. So for now on, we simply say the rank of A. there's no reason to say the row rank or the column rank, because they're the same. If the row rank of A is 7, well then, according to this theorem, unproven theorem, the column rank of A is also, I forgot what I said. I think I said if the row rank of A is 11, well then the column rank of A is also 11. They're the same answer. So why not just talk about the rank of A? Okay, so no more row rank, no more column rank. We just talk about the rank of A. So I give you a matrix A, and I say find the column rank. You can say, you know what, I'm going to find the row rank, and whatever I get, I'm going to say it's the column rank. They're the same. They're exactly the same. Now, to find the row rank of a matrix, fortunately, is very, very simple. You just have to know how to reduce a matrix. If you know how to reduce a matrix, it's very simple. To find the rank of A. Very simple. Step 1. Reduce A to B in RREF form. That is, B is in RREF form. And then we're done. Step 2 is trivial. The rank of A is equal to the number of non-zero rows in B. So you count the number, you reduce A to RREF form, which I'll call matrix B, and then you count the number of non-zero rows in B. In other words, again, make believe this is true. If A is 1, 2, 3, 4, 5, 6, 7, 8, 0, 2, 4, 6, and it reduces to the following matrix. 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay? So now I'm done. I can answer. That was step 1. And step 2, I hope you realize is trivial. Once you reduce matrix A to something in RREF form, just count the non-zero rows. Well, this is a 0 row. So there's 1, 2 that are not all zeros. Okay, so the rank of A is 2. And of course, I pretty much bet my life on it that this matrix is not reduced to that one. Okay, but we make believe. If that troubles you, not a big deal. I'll just state it just ever so slightly differently. There must be some matrix A that reduces to this. In fact, this matrix is not in RREF form. Okay? Because the row that had all zeros, I have to put in the bottom. Okay? There are 2 non-zero rows, so the rank of A is 2. Now, I think I said, I guarantee myself that there's a matrix A that reduces to this one. And the answer is, yeah, of course. I can always use this matrix. I can always use that matrix. It's row equivalent to this one. And you want to say, but that doesn't count. It's the same matrix. Wonderful. Wonderful. This matrix here is not in RREF form because that second row is all zeros and it's not on the bottom. Oh, okay. I'll switch these two, and then I get this matrix here. You can always find a matrix that's row equivalent to this one. Okay, so just reduce the matrix A to RREF form and count the number of non-zero rows and say the rank of A equals that number. So if you know how to reduce a matrix, you can compute the row rank. Okay, doing examples, I don't think that's beneficial because all you have to do is count. I mean, an example would only help me teach you how to reduce a matrix. But I'm hoping that by now you know how to reduce a matrix. Just reduce the matrix and then count the non-zero rows. Okay, just count the non-zero rows and say, boy, that was simple. Now, remember, we talked about the nullity of A. Nullity of A is equal to the dimension of the null space of A. What is the null space of A? The null space of A is the set of solutions to AX equals 0. Oops, not so sure what happened. But the null space of A is the set of solutions to AX equals 0. Okay, that's the null space. And we can talk about the dimension of that null space. And once you start talking about the dimension of the null space of A, you're really talking about the nullity of A. And now, I'll sneak it in here, we have this major theorem. If A is an n by n matrix, then the rank of A plus the nullity of A is equal to n. The rank of A plus the nullity of A is n. And this is a theorem. We're not going to prove it. Read the proof in your textbook. I'm sure it's there. It's a nice proof. It's definitely doable. So how about we verify this theorem with the following? Verify this theorem with this matrix A. This here is 5 by 5. That theorem above, it's only for a square matrix. If you reduce A, so before I go on, this n is that number. You hate that number, then it's that number. That is, n is 5 in that theorem. Okay. If you reduce this matrix, you get the following matrix: 1, 0, 2, 0, 1, 0, 1, 2, 0, negative 1, triple 0, 1, 2, and then 2 rows of 0. The rank of A is 3. Now, remember, if you're trying to find the row rank, you're supposed to take these 5 vectors and write them as columns and reduce that. But if you're doing the columns, you want to find the rank of the columns of those 5 vectors, those 5 column vectors, then you don't have to transpose. Well, we don't want the row rank of A. We don't want the column rank of A. We just want the rank of A. But the rank of A is both of those. The rank of A is the column of A. It is the rows of A. It is the row rank of A. That is, you don't have to transpose this ever. You reduce it, you get 3 rows that are not entirely zeros. That's the rank of A, 3. And the nullity of A is the number of rows that have just zeros, which are 2. And if you add up these 2 equations, you have the rank of A plus the nullity of A. Due to space, I'll write R for rank. Rank of A plus N for nullity of A is equal to 3 plus 2, which is 5. And it was supposed to equal N. The rank of A plus the nullity of A is supposed to equal N. And in our case, N is 5. Reduce it, count the number of rows that are non-zero. That's the rank of A. Count the number of rows that are 0. That's the nullity of A. Well, of course it's going to add up to the number of rows, because there is no row that is both all zeros and not all zeros. Either that row is all zeros or it's not all zeros. So basically, you run a little tally. You have not all zeros, all zeros. Okay, row 1 does not have all zeros. Row 2 does not have all zeros. Row 3 does not have all zeros. Row 4 has all zeros. Row 5 has all zeros. So the rank is 3 and the nullity is 2. Of course it's going to add up to the number of rows. There's no way out of it. Okay. Next statement. You should start realizing that we have new ways or new equivalences for a matrix to be non-singular, for a square matrix to be non-singular. We have new equivalences. We call the following. We call that a square. Okay, let's try that again. We call that a square. n by n matrix A is non-singular, that is, it has an inverse, is non-singular if and only if A is equivalent to the identity matrix. Okay, now a lot of theorems or one theorem and a lot of consequences, corollaries. So now we know that an n by n matrix is non-singular if and only if the rank of A is n. Because every time in an n by n matrix, if the rank of A is n, that means it has no rows or zeros. Okay, because remember, the nullity of A, which I'll call unknown, plus the rank of A, which is n. Well, when I add the right sides, I get n plus x. When I add the left side, I get the nullity of A plus the rank of A. I get nullity of A plus the rank of A. But that's supposed to equal n. This is supposed to equal n. For x is 0. Okay, there are no rows of zeros. There are no rows of zeros. And every time you take A and you reduce it to a matrix who has no rows or zeros, you always get I. You always get I. That is, this is equivalent to A is row equivalent to I. But that's exactly what it says above. An n by n matrix is non-singular. A n by n matrix is non-singular if and only if A is row equivalent to I. But that's exactly what this means. Okay, so if you can reduce, if the row rank of the square matrix A, the n by n square matrix is n, let me start over. If A is an n by n, and the rank of A is n, then the matrix A is non-singular. It's non-singular. Right? I pretty much gave the proof, at least the concept of the proof. You want to show that if the rank of A is n for an n by n matrix, then A is row equivalent to the identity. So anything that's equivalent to A being row equivalent to the identity is also equivalent to the rank of A equaling n. We have the rank A equal n. We have A is non-singular. And we have A is reducible to the identity matrix. And for all of these, A is n by n. Well, these two are the same. Those two are the same. That is, this and that, no difference. And these two are the same. This is exactly the same as that, and it's exactly the same as that. This is exactly the same as this and that. Well, of course, these two will be the same. They're exactly the same. If x and y both equal z, then x and y have to be equal to one another. If I say I didn't get or be or below on the last test. Well, that's the same as I got an A on the last test. Those two were the same. I mean, either you get an, well, we'll forget A minuses and B pluses, just A, B, C, D, and F. No incompletes, please. If you didn't get a B or less, you can get an A, or B, or C, or D, or an F. You didn't get B or less, that means you got an A. These two are exactly the same. I got at least a 90%. Or assume that any 90 and above are A's and nothing below 90 is an A. As an 89.99 average, you don't get an A. So this third line implies or is the same as I got an A. Well, of course, then the first and the third are the same. I didn't get a B or below. I got at least a 90. They're exactly the same. All right, so as promised, let's write up some of these wonderful corollaries. Okay. If A is n by n, then the rank of A equals n, if and only if the determinant is not 0. How do I know that? Because if the rank of A is n, I know that A is non-singular. And if A is non-singular, then the determinant of A is not 0. Another corollary. If A is n by n, if A is n by n, the linear system AX equals B has a unique solution. Well, I know that AX equals B has a unique solution only if and only if the determinant of A is not 0. But the determinant of A not equal to 0 is if and only if the rank of A is n. This is called putting the rank of A in n. I left the K out, sorry. Just putting all the ideas together. The rank of A is good old n. So what we're going to do now is update our list of equivalences for non-singular. Non-singular equivalences. And every time I write down the matrix A, it means A is n by n. It's understood. List of non-singular equivalences for n by n matrix A. First one is A is non-singular. That's the same as AX equals 0 has only the trivial solution. A is an n by n matrix, and it's row equivalent to the n by n identity matrix. AX equals B has a unique solution for every n by 1 matrix B. Determinant of A is not 0. If you come to know the determinant of A is not 0, then A is reducible to the identity. And A is non-singular. And AX equals B has a unique solution. Here are some new ones. The rank of A must be n. Well then, the nullity of A must be 0, because these two have to add up to n. If this were n minus 1, then the nullity would have to be 1, because they have to add up to n. The nullity of A plus the rank of A must add up to n. So if one of them is n, the other has to be 0. And here's a couple that we didn't really speak about. It says the rows of A, remember, is n by n. The rows of A form a linearly independent set of n vectors in Rn. The rows of A, which has n, there are n rows, and they're all linearly independent. That means when you reduce it, you're going to get the identity. You're going to get the identity, which means it's non-singular. It means all others. And number 9, okay, so that's number 8. Number 9 is the columns of A form a linearly independent set of n vectors in Rn. This n is that n. That n is this one when I'm talking about columns. Okay, so we're up to 9 equivalences, and know them. That way you can go from one to another. If you know the rank of A is not n, it's less than n, don't look for the inverse. Don't augment A with identity matrix and then reduce it, because you're not going to get an inverse. Okay, on to theoretical exercises. 2 being the number 2. I'm going to do 2 of them today. Okay. This is a nice problem. Let A be an M by N matrix where M and N are different. Show that these are the rows of A, or, that's the mathematical or, it can mean and as well. Show that either the rows of A or the columns of A are linearly dependent. A proof. Without loss of generality, assume M is less than N. You can do this proof twice. First, assume N is less than N, and then assume that N is in Nancy is less than M, as in the name Mary. But I'm not going to do that. Now, what is the rank of A? Now, the row rank of A has M rows. So it's going to be M or less. And the column rank of A is less than or equal to N. So M was smaller. Let's concentrate on this a moment. Either the rank of A is equal to M or it's less than M. We're going to look at both cases. If the row rank of A is less than M, well, then we're done. Then the rows are not independent. Then the rows of A are linearly dependent. On the other hand, if the row rank of A is equal to M, okay, is equal to the M, that implies that the column rank of A is equal to M. Because whatever the row rank of A is, it's certainly the column rank of A. But M is less than N. That is, the column rank of A is less than N. That means the columns are independent. That implies the columns of A are linearly dependent. And that completes the proof. Do another problem. It's a fun problem if you make connections easily It's a very easy proof. But you have to get your hands dirty. I'm not doing any magic in these problems other than stating definitions most of the time. Okay. Show that if A is an m by n matrix, such that A times A transpose is non-singular, then the rank of A must be m. I might have a little mistake there, but we'll find out in a moment. Proof. A is m by n. That implies that A transpose is, the switch D's, is n by m. Then A times A transpose is, well, A is m by n by A transpose, which is n by m. And since those are the same, we just get the outer, m by m. Okay. Yeah, I guess this is a little typo. This should be A times A transpose. Okay. A times A transpose is one matrix. You multiply two matrices, you get our matrix. This is one matrix. And if this matrix is, and it's an m by n matrix, A transpose is m by n. If A times A transpose is non-singular, that implies that the rank of A transpose is m, excuse me. And that completes that proof. And it also completes their section on the rank of a matrix.